Right. Good morning, everyone. I hope that you can hear me. If I could just have one person respond that you can hear me.
Yes, I can hear you.
Okay,
Yes, we can
perfect,
hear you.
perfect.
Yes, we can
So
hear you.
on your screen, I hope you can see in front of you kind of details on the molecular modeling prac that we're going to be dealing with. It's at the very bottom of the Are You Connected uh, site for 301. You go right to the bottom. There are two things that you need to look for. One is a PDF or PowerPoint, depending on what you prefer, that has details on how to use Webmo. And then the second thing you need to look for is the actual task that I want you to do. Now, you will have to do everything that is on the instructions on the PowerPoint or PDF before you can start the prac. And part of what you do from the PowerPoint will count towards marks in the prac. So have a look at those. I detail exactly what you have to do. And so you can follow it through, and I will be able to see what you have done on the site. We are using, so just please note, if you can write this down right now, because I haven't got this freely available. If you don't write it down, you will have to email me to get this password. And the password is case sensitive. Now, to get to Webmo, I suggest if you would prefer to use a cell phone, please install the Webmo app. It is a free app. You do not have to upgrade to premium version to do this practical. If you run into any trouble with it, please just email me. One thing that I do want you to figure out how to do is to take snapshots, pictures of your cell phone, so that you can send pictures of the results to me as part of the hand-in for the prac. So please figure that out. On my Huawei, to take pictures of a cell phone, I press the turn on bottom and the volume down button together, and it just takes a snapshot of what's in front of me. I've done this prac both on using a web browser on my computer and on my cell phone, and it seems to work fine for both. So you're going to go to calcium.ru.ac.za, which is my server. Please, on Calcium links you to two versions of Webmo. One is my own version of Webmo, Webmo Standard, and I don't want to use that because although you've got unlimited time and you can do some really high-level calculations, you don't have access to some of the properties that we would like to calculate in this practical. So I want to use the hope.edu web server, and so you will go to Webmo Pro from Calcium, and then you will see a login screen that looks much like this. If you are on a computer, you just type in the username and the password, which I've given you here, straight away. If you're on a smartphone and you've got the app installed, go connect using the Webmo app, and then your cell phone will look something like this. And you can see my username here. I've stripped the leading G off my student number, or this is a random student number. I've stripped the leading G off it, and I've used a capital L as the letter, and that then should get you to log in. So follow the slides through. I've got where it's relevant for a cell phone. Just look for the picture of my cell phone, how I've done it, and that will show you how to do molecular modeling using either web browser or your cell phone. So that prac, whether it's done now or whether it's done when we get back, will be ultimately for marks. There's no deadline because we don't know when we're going to be back. But please, if you can do it as quickly as possible, then there's less to do later in the year. And that gets one practical out of your way. Are there any questions? Okay, if there are no questions, I'd like to then just go back to the lecture slides. Just hang on a moment while I get to the lecture slides. Um, this takes up more than my screen, so I have to go off my screen to find the lecture slides. And let's go back there to quantum mechanics, molecular modeling. Okay, so yesterday we had a look at the Z matrix, and the Z matrix is quite interesting. It provides less numbers to work with for computers than Cartesian coordinates. In fact, it provides 6 less numbers to worry about because it takes away translational and rotational information. And of course, the first line of a Z matrix is simply an atom symbol. The second line has a symbol, a connectivity info, some connectivity info, and a bond distance. So there we know that the bond distance from 2 to 1 is 0.96 angstroms. And the third line will not only have bond distance info, but it will have bond angle info in it. And as you get into a Z matrix, it only goes up to dihedrals. So the worst you can have in a Z matrix is with a bond distance, an angle, and a dihedral. No other angles, no other numbers get added onto the end of lines for the Z matrix. Okay. So now we have dealt with defining the problem and constructing the model. I'd like to move on to doing the calculation. And there are 2 ways to do the calculation. In the lectures, I'm going to work with molecular mechanics. In the prac, right behind all the calculations, when you
Say,
tell it to calculate, it's going to be,
sorry,
yes, hello?
can you please explain the way we construct the molecule one more time before we move to the calculations?
Uh, you mean how to construct the molecule? Um,
Yeah, like how to use those symbols and angles, how to construct a molecule using those the
so
information given up.
Okay, so if you don't, if you're struggling with the Z matrix, please can I ask you to go to the first slide on the Z matrix in the handout, where it's drawn like this, and then follow it through where you've um, labeled the atoms by number. And so I've picked any atom as the first uh, as number 1. So I've chosen the oxygen as number 1. And so my first row has an oxygen. And then you then pick another atom. And now because it's in relation to atom number 1, you can now input that it's bonded to atom 1 with the distance of the bond distance. And then finally, uh, we can put the third atom in, which not only is bonded to atom number 1 with the bond distance, but you'll see that it also has a bond angle 312, 312 of 109.5. So please have a look at that. In terms of uh, constructing the molecule, uh, uh, we don't have too much time, but maybe if you're still having trouble, get hold of me outside of a lecture and we'll have time to go through it. Okay. Um, in reality,
Okay.
in reality, what happens is that um, you'll find that when we do the prac, you don't have to build up these Z matrices yourselves. I will never ask you to build up a Z matrix for a very complicated molecule. Anything greater than 4 atoms, I'm not going to place that um, on your plate. It's a tough thing. I won't even try and do that myself. What I do is I try and use a mouse or whatever tool I have to construct the molecule. If I need the Z matrix, I'll then ask the software to provide it for me. So you'll be able to see that when you use Webmo, after you've built furan, or if you've built ethanol or even water, you will be able to look through one of the menus and ask it what is the Z matrix, and it will provide it for you. Okay, so um, the Z matrix is available. Other softwares prefer to have the molecule in Cartesian coordinates. So after you constructed it, you can look at the file and you can see the XYZ coordinates available. But ultimately, You construct a molecule, and it has to be represented in some way. Graphic is good for us, but the coordinates are good for computers. So Z-matrix and Cartesian coordinates are good for computers. Okay. Now, when you use Webmo, and you ask it to do a calculation, some server is going to be doing some calculations, some quantum mechanical calculations for you, and it's going to provide you with a number at the end, with a geometry or an energy value at the end that has been calculated purely using the principles of quantum mechanics. I'm not going to deal with how that, with the principles behind how the computer does that at this point. I'm going to have a look at a simpler way to try and calculate energies and geometries of molecules called molecular mechanics. And molecular mechanics, even though it's not as accurate as quantum mechanics, is still very, very popular today. So molecular mechanics tries to find a way to estimate the energy contained within a bond, not when the bond is at equilibrium, but when you try and move it away from equilibrium. And the best way to estimate the energy is to model a bond as a spring, because you can use Hooke's law to translate the force constant and the displacement of that spring into an energy value. So from physics, there's just an x squared multiplication that you have to do, and you've got an energy value very, very fast. It's scalable to thousands of atoms, so you can work with proteins, and there are many properties of molecules that you can calculate with molecular mechanics. So certainly you can get to an optimum geometry. I'll tell you what conformational searches are, and I'll tell you what normal modes of vibrations are a bit later on. But ultimately, the term of molecular mechanics is a total energy that's in terms of a sum of bonded terms and non-bonded terms. So if you have a look at the bottom, you've got your energy, your total energy for a molecule is the sum of energy due to stretches or bends or torsions. And there's some non-bonded, the electrostatic and van der Waals. And you add all those terms together, and you'll end up with the total energy of your molecule. So the question that people had many, many years ago is, if you've got a molecule, how on earth can you get the energy maybe due to displacement of a bond? And the thought was, well, let's imagine a bond as being two atoms connected by a spring. And of course, a spring always has an equilibrium distance. If you relax a spring, it wants to be at a certain distance, a certain length. And so you can define that energy as being energy naught and having zero energy. And of course, if you displace to the right, the energy will go up, and you can relieve that energy by moving back. If you displace, if you compress the spring instead of stretching it, again, the energy goes up, and it will want to relax back. It will want to relax back to equilibrium. From physics, Hooke's law says that force opposes displacement, and that you can get an energy for the spring of a half of the spring constant times the displacement squared. Okay, but in terms of a bond, if we want to translate that in terms of a bond, the displacement is not an x squared. The displacement is a difference from equilibrium. If your distance is not at equilibrium, that difference, it is away from equilibrium, is your displacement, and we can square it to get the Hooke's law equivalent energy. What we need to do, though, and we'll find out a bit later in the second set of lectures, is how to get to these force constants for atoms, because you cannot simply take a pair of atoms and move them apart and experimentally measure that energy. That is a very difficult task to do. So the form of the energy within a bond is simply a force constant for those two atoms for that bond times the displacement or the difference from equilibrium all squared. And that works quite well. The thing is that this is a quadratic, and so the form of the potential energy surface that you get, if you say a bond has an energy in this way, remember a bond doesn't really have energy in this way. We're just trying to pick a function that will approximate the energy within a bond. But if you say a bond has uh, energy in this way, then the profile as you move the atoms closer and further apart is as follows. In reality, um, if you try and stretch two bonds, if you try and compress two bonds, it will follow this parabola very closely. You see there's a slight difference. See this solid line up here is how atoms really behave. If you move them closer and closer together, at some point they will exceed that quadratic potential energy surface. And so there is a problem that what this function we have chosen doesn't perfectly match. But close to equilibrium, you can see they're very, very close together. And so in most molecules, this potential energy surface will work fine. The biggest problem comes if you try and pull atoms apart. Because if you say that the energy goes up as your displacement goes squared, then as you try to move atoms further and further apart, the energy will go up further and further and further. It will never come down. X squared doesn't get smaller as x gets bigger. And so our function is telling us that we can't, that the further apart those atoms are, the higher the energy. You cannot, and the higher the energy, the more it's going to want to go back towards equilibrium. So what this function does is it prevents us from breaking bonds. In reality, we don't have such a steep increase in energy as you move atoms apart. The increase is much more gradual, and eventually, if you move atoms further apart, you will be able to break them. Okay, so our x squared function is a very simple function. It doesn't quite match reality, which is a Morse potential. However, close to equilibrium in this region down here, which is where we are most interested with molecules, it matches very well. And so it is good enough to use. So I'm going to go back a slide and just remind you that to calculate the energy of a bond, you need to have a force constant for that bond. You need to be given that number. And then you also need to know the current distance that those atoms are apart and the equilibrium distance, the best distance for them to be apart, and then you can calculate the energy for the bonds. But this here is only the energy for one bond. If you've got a molecule, your molecule might have many bonds in it. I've given an example here of a molecule which has 5 bonds. You have to add all of those energies together to get an E stretch term. So I would have to do that K into R minus R naught all squared 5 times for this molecule to get a total, to get energy for each one of those bonds. And then I would have to sum all 5 of them together to get the energy due to stretching in this molecule. So in molecular mechanics, yes, it's a simple function per bond, but you must not forget to add in all, to do the calculation for every bond in your molecule. Be careful, because if you've got an oxygen and a carbon, that K is going to be different and the equilibrium bond distance is going to be different. So you may need a whole list of K values and a whole list of equilibrium bond distances to be able to do it for a molecule, to be able to calculate the E stretch term for a molecule. Now, in a similar way, we can look at, hang on, I just first do an example. So there's a very simple example here of a molecule of water, but of course, you might notice that the angle is not perfect at an equilibrium angle, and certainly the bond distances are not at an equilibrium bond distance. If you have a look at parameters that are available for an OH bond, I've managed to get out some parameters, and the K for an OH bond is 553, and R naught for an OH bond is 0.96 angstroms. So you can tell immediately that if you wanted this to be 0, you would have to make this term exactly, this bond distance be exactly 0.96 angstroms. If it was exactly at an equilibrium bond distance, this term would then come to 0 and your energy would come to 0. Have a look at this molecule here. You see that neither of these bonds are at 0.96 angstroms, so both of them do not have 0 energy, and we can calculate it. And so you can simply put the 1.26 into this equation, or the 0.66 into this equation to calculate the energy to this bond, or the energy due to that bond. And I have done that. So for the first bond, I've placed 1.26 in. The second bond, I've placed 0.66 in. And this is an interesting choice of conformation for water, because the stretch in this bond is same as the compression in this bond, such that the energy, strangely enough for both of them, has turned out to be exactly the same. In general, it won't be exactly the same, but ultimately you need an energy value for every bond in that molecule. And when you sum it, the sum is simply two terms. We just need to add these two numbers together to get a total energy for the molecule of 99.6 kilocalories per mole. And obviously, this molecule isn't going to want to stay in this case. It would, if we were doing a calculation, we might do a geometry optimization. And in the geometry optimization, we would slowly lengthen this bond until the energy dropped down to 0, and we would shorten this bond until the energy dropped down to 0. And you would find in your equilibrium geometry that these bond lengths would both be at 0.96 angstroms at that equilibrium bond distance that we wanted. Okay, now in a similar way, we can treat angles in a similar fashion, although it's not exactly a Hooke's law situation. We get a really nice energy function if we follow the Hooke's law principle with that, in that when you stretch an angle beyond what it should be, so if your angle should be at 120 degrees and you've stretched it to 160 degrees, the energy must go up. And that energy is going to be a driving force that pushes it back to equilibrium. And similarly, if you compress it, the energy must go up, and that's a driving force that makes it go back to equilibrium. Anyway, the form that we build up for bend terms is simply we have a force constant again, and that force constant is the actual angle, which is not where it should be, minus the equilibrium angle, which is where it should be, all squared. So the form for the angle for calculating the energy of a bond angle is exactly the same as for calculating the energy of a bond, though of course those K's are going to be different. Don't forget with bend terms that a molecule will have many angles in it. So here is my molecule, and you can see there are 6 angles in that molecule, and so we would have to add 6 values together, bearing in mind that if these atoms are all different, these angles may have different K values, and they may also have different um, equilibrium angles. So there's a lot of work in this molecule to calculate the angle energy, the E-bend term for the molecule. There are 5 terms that need to be calculated individually. So just as an example, we go back to that water molecule, and we've dealt with the bonds, but it'd be interesting to look at this angle. And if I look in the software and what is used for E-bend, so for an HOH water bend, it's 100 kilocalories per mole per radian squared into theta minus whatever 104.5 degrees is in radians. So the equilibrium bond angle is 104.5, but you must convert to radians. The K term is always given in radians. Okay, so we can do that. We can do this calculation. The first thing we've got to do is convert our 109 degrees, 109.5 degrees to radians. When we've got 109.5 degrees as radians, we can then calculate the energy due to that bond angle. So you can see here, E is K into theta minus theta naught squared. Theta here is our 109.5 degrees that we've got here in radians. Theta naught is the 104.5 in radians. And of course, we get an energy term. And you can see that that slight displacement from equilibrium is not as harsh in terms of energy increase as those compressions and stretches of the bonds that we had. Okay, so this is the energy due to this single angle. But if you want to calculate the E bend term, you have to sum up every single angle in the molecule, which fortunately in this case is only one term. So our total energy E bend for this molecule is 0.774. Just a minor point. I said at the start that in molecular mechanics, the total energy is the sum of bonded and non-bonded terms. And actually, for water, all other terms that we haven't dealt with, the values are zero. These are the only two non-zero values for water. So we can calculate the total energy of this water molecule because we've calculated the stretch term from all the bonds. We've calculated the bend term from all the angles. And so the total energy for this water molecule is 100.4 kilocalories per mole. Now, just a little point is that I will only ever ask you to do manual calculations like this using the stretch and bend terms. I will not ask you with the more complex terms to calculate energies of molecules. So please have a look on Are You Connected? The task you have on Are You Connected is to have a look at cyclopropane and cyclobutane. Now, in cyclopropane and cyclobutane, those bond angles are forced to not be at the equilibrium bond, equilibrium angle that we would expect. So there is some energy contained in all of those angles. And so I've given you enough information. I've given you the K term. I've given you the theta naught term on Are You Connected? Now, what I want you to do is to calculate the energy due to the CCC angles in both cyclopropane and cyclobutane. Okay. Now, for other terms, what I want you to do with other terms is I want you to get an idea of the problem faced when trying to build up energy terms. We have really thumbsucked these forms of a potential energy surface to use in a general situation. They're not accurate. They don't. They're not very, very precise, like we would get from quantum mechanics in terms of getting an exact energy. But they are very, very good and efficient at getting to equilibrium geometries and doing conformational searches and other types of calculations. The question is, how can we deal with other parameters beyond just stretches and bends? And to illustrate the problem that we have is that when you look at torsion angles, in some systems, if you look at, for instance, an amide bond has two positions. There are two maxima. If you rotate it through 360 degrees, you should have two maxima 180 degrees apart. However, in ethane, or in an aliphatic system where you've got sp3 carbons connected together, as you rotate the bond, there need to be three maxima as you go around. And it's interesting to note that a mathematical function that allows us to have many maxima and minima as you go around is a cosine function. And so people doing molecular mechanics have hijacked the cosine function to estimate the energy term due to rotation around a bond, a torsional energy, energy due to a dihedral angle. So please don't take this as being the ultimate energy in a molecule, absolute energy, but it is a function we have appropriated to be able to estimate the energy due to rotation about a bond. Okay, so just as an example, I would have liked to use hydrogen peroxide as an example, but hydrogen peroxide actually has two maxima and minima, and I was looking for a system that has only one maxima as you do a rotation. You'll see what I mean in a moment. So I've constructed here a hypothetical molecule that only has one maximum and one minimum as you rotate around this 2,3 bond. So to be able to deal with this molecule, we need to look at a Newman projection of it. I'd like to look down this bond here from the 2 to the 3. And so this view on the right-hand side is me looking at it on that. So let us say, for instance, that our hypothetical molecule has a minimum and equilibrium dihedral angle at 115 degrees. What that means is that if you rotate the groups around to any other value, you get a higher energy, but at 115 degrees, your energy is at a minimum. Okay, then you can see how a cosine function would fit this very well, because as you rotate it around, it simply matches, and you get one maximum per rotation, and as it comes back, you eventually get back to its minimum at 115. Note that I've gone through 360 back through naught, and so this just cycles around from 360 back to naught, back to our 115. So the question is, how could we build up this exact function from a cosine term? Well, a cosine looks like this, which has a minimum at 180 degrees, not at 115 degrees. So here's our cosine function. Our cosine function has another problem, is that it has a negative value, and we do not want our system to have any negative energies. We want the lowest possible energy to be zero, our equilibrium dihedral angle to be zero, and every other energy to be greater than that. So a cosine function almost matches, but it's not quite there. So cosine goes between 1 and -1. So first thing we can do is we could add, if we add 1 to our cosine function, then we at least get a cosine function that is positive everywhere, but it still has two problems. It does not have a minimum at 115 degrees. And of course, the energy might not be 2 kilocalories per mole per radian as we go around. So we need to change the cosine function still further. So what we could do is we could divide that by 2 to scale it down to 1, and then scale it up to the exact energy value we want. So if we multiply all of that by v over 2, we can make sure that the cosine function goes to a maximum potential energy that we want it to, and not to a maximum of 2, and certainly not any negative energy values. So now we're almost there. The only problem left with the cosine function is that its minimum is not at 115. And so the way we can sort that out is we can add a phase angle to the cosine function. If we subtract a number before we do the cosine, then the cosine will not be centered at 0. It'll be centered at the exact point we want. And so that adding that phase then shifts the cosine function to make it look like what we want it to look like. So what I'm trying to show you here is that if we want to calculate or estimate the energy due to a torsion, firstly of all, an x squared potential energy surface is not going to cut it because we're going to need some maxima and minima. Secondly, that we have to adjust a cosine function in some way that it represents not only the maximum potential energy that we have in that rotation, but also the phase in that rotation. Just another example, just to maybe illustrate how building up this cosine term is a complex issue. Have a look at ethane. This is simply ethane. And we don't have one maximum per rotation as before. You'll see that as we rotate it around, you can see as you move it, the energy comes down, and you've got staggered ethane at its lowest value. And then, of course, it goes up as you become eclipsed again, and that carries on. Now, in this case, a cosine function still has a problem, is that it's only got one maximum per rotation and not three. And of course, we've got the problems of a maximum potential energy, and perhaps there may be a phase in some systems that's not included. So the first thing we will do to the cosine, we have to modify the cosine to make it fit our purpose. And the way we modify the cosine in this case is to have the cosine of 3 times the torsion. If you've got cosine of 3 omega, then you end up having 3 maxima, which is what you need when you rotate ethane. Now, similarly, you can't have negative energies, and so you're going to have to add 1 to that cosine function. And then you've also got to scale it to get the right maximum of energy to that, and you might even have to add a phase angle to it to get the final torsion term. Okay. Now, if you thought that was not bad enough, sometimes a cosine function is not even good enough to represent a torsion term. Okay, and at this point you'll realize that I'm not going to ask you to remember exactly the full equation that we've got here, but have a look at an amide bond. With an amide bond, there are both, you'll notice there's a trans arrangement of an amide bond, and you've got a cis arrangement of the amide bond. Both of those are minima on the potential energy surface. However, the cis arrangement is a higher energy minima than the trans arrangement. And so this is not a cosine function at all. So this is a case where even a cosine function has broken down. But we can, in some cases, we can build up this potential energy surface by adding more than one cosine function together. So this exact potential energy surface is built up by adding 2 different cosine functions, both with different periodicities. Okay, so building up the torsion term is not a straightforward task. We have to use a cosine function in some way for torsional energy. For torsional energy, we have to have an n value, and that n value determines the periodicity. If it's 1, we've got 1 maximum as you rotate through 360 degrees the torsion angle. If it's 2, you've got 2 maxima. If it's 3, you've got 3 maxima. We may have to include a phase to shift where the minimum is. And certainly, we have to do the 1 plus and the scaling to make sure that the maximum energy is not 2, but the maximum energy is the maximum energy we want it to be. So this here, if you remember that this here is the form for torsional energy, but that you might have to add many of these terms together, that is sufficient. But I'm certainly not in this course going to ask you to apply the torsional energy term to any molecule. It may be not that, if you're given all the values, it may be quite feasible to do, but the time is not worth the effort. Rather, let's allow computers to do that. Let's remember that the form is like that with the cosine term in, but rather let's let Webmo or whatever software you're using calculate the form of that torsional energy. Of course, in a general molecule, there are many torsion angles. So can you see this red torsion angle in this molecule? That red torsion angle is at about 0 degrees. And that 0 degrees might not be the equilibrium torsion angle that you're looking for. And so there might be a cost to having that arrangement for that red torsion like that. And similarly, that green torsion, you can see that green torsion is at 180 degrees. Again, that might not be at equilibrium. We'd have to calculate both of those energy values due to the torsion, and there are another two as well. And so the E-torse turn would be the sum of four values, bearing in mind that each one would be quite complex to build up. Okay. So those are the bonding terms in molecular mechanics. And um, so your bonding interactions, you have to calculate an E-stretch, an E-bend, an E-torsion term, add them together to get your bonding interactions. And maybe I can just quickly speak of the non-bonding interactions, van der Waals and electrostatics. These are our steric interactions. So van der Waals will be our steric interactions. And of course, electrostatic, all atoms will have a partial charge, and so they will be attracted or repelled from each other. With van der Waals, again, I'm not going to ask you to do calculations with van der Waals, but I want you to note that if you move atoms very closely together, they repel each other. However, so you can see if you take two xenon atoms and you move them, try and get them too close together, the energy goes up and up. They try and push away. You've got those electron clouds interacting. However, if you take two xenon atoms and you move them further apart, the energy goes up from a minimum. Those xenon atoms are going to want to be a certain distance apart. It's attractive. If you've got two xenon atoms at this point, they're going to want to attract until they get to an equilibrium distance from each other. So van der Waals are attractive from a far distance, but repulsive when they're close. And a function that people have thought up that seems to match this quite well is a Lennard-Jones potential, which has something to the power of 12, a very high repulsive value. Something to the power of 12 scales really, really high. And then something to the power of 6, which is not quite so powerful, a very weak attraction for the long distance. So this Lennard-Jones potential works quite well. And if you choose the right values, you get a good estimation of how non-bonded atoms should attract each other, or how they should repel, what the steric interaction should be if they come into close contact. And then, of course, atoms will have partial charges, and those partial charges could be like or unlike. And of course, if they are like, you'll see that if you've got an atom that two atoms that have the same charge, the energy goes up and up if you try and push them together, and they will want to move apart. However, if we've got unlike charges, the energy, you'll see it wants to go. The energy just keeps dropping as those move closer together. But of course, the exact form of the energy is using a Coulombic type equation to calculate the energy due to that electrostatic attraction. So you mustn't forget, though, also with your non-bonded terms, you have to sum over all pairs. And this horrible looking double sum here, all it means is that if you want to get the electrostatic term, you've got to look at all pairs and calculate the electrostatic interaction between the two, the energy for every pair. You've got to calculate the van der Waals for every two. And you'll see that this is just the Lennard-Jones that I had on the other side, and this is just the Coulombic I had on the other side. So this perhaps is not necessary in principle to put down. What I really want you to know is that it's a sum of electrostatic, which is, the electrostatic is a sum over all pairs, and the van der Waals is a sum over all pairs. As a final note, in molecular mechanics, we've got the sum of bonded terms, which include stretches, bends, and torsions. We've got non-bonded, which includes electrostatic and van der Waals. We add them together, we've got the energy of our molecule. However, some people don't think that's enough, and so There are some unusual terms in some cases. I don't want to spend much time on them, but you can imagine if you've got a carbonyl group, um, if you've got a carbonyl group, you can see a carbonyl group with an arrangement like this is not ideal. And so you really want a carbonyl group to be planar. You can imagine if your carbon and your oxygen are not in a plane, you need a term, you might want a term that forces them to be planar. And so some people add an out of plane term that is dependent on the angle away from the plane. Some people do calculations involving cross terms, and the best example of this is with water. If you try and force the angle in water to get smaller and smaller, the bonds of the HO bonds in water get longer to compensate. So you might want to then change your equilibrium bond length if you're changing the bond angle. So cross terms can enable that to happen. But these are unusual terms, and so I don't want to concentrate on them, but I want you to be aware that other people may do the calculation to try and get a more accurate total energy. They might try to add some unusual terms into it to get a total, more accurate energy. So in molecular mechanics, what you do is you calculate the total energy based on bonded parameters. Each one of these is a sum, and your non-bonded parameters, each one is a sum in itself. And of course, some people may use a slightly different equation. The equation, the exact equation that is used to calculate the energy and the Ks and the equilibrium all together is termed a force field. And so some examples, so the K values I've given you in this lecture come from the amber force field, but there are other sets of values like the charm force field and the Gromus force field. Now, just something for you to think about. You can imagine that if you're looking at simply the bond parameter, so carbon-carbon bond, the energy is K into R minus R naught squared, the displacement squared. We'd need to know the K and the R naught for that carbon-carbon single bond. We'd also need to know a K if you had a carbon-carbon double bond and a different R naught, of course. And of course, those values would be different if you had a triple bond. What about an aromatic bond? A partial bond? What if you change to now C oxygen? What are the options with that? But we've got a periodic table which has 92 elements. And of course, the number of single bonds might be 92 squared. So you can quickly see that you need lots and lots of different parameters depending on the two atoms that you're working with and depending on the type of bond between those two atoms. So the lack of parameters can be a problem because certainly I don't think any software has a list for all 92 elements times everything they could be bonded to. So lack of parameters can be a problem, but still parameters are available for common systems. Certainly with proteins, parameters are very, very well characterized and are available. Okay, so just to give you an example where we are, I've discussed defining the problem, constructing the model, and how that model is represented in terms of Cartesian coordinates or the Z matrix. And now I've just given you a taste of how you can estimate the energy of a particular molecule simply by looking at the bonds, the angles, and the torsions, and maybe non-bonded bits between. Okay, so we'll move on to other aspects, but to check that you understand how to some of the concepts in this lecture, I want you to have a look at the Are You Connected quiz, which looks at cyclopropane and cyclobutane. Okay, are there any questions? Any questions? Yes. Yes.
So for the course, are we only expected to be able to calculate the bonded terms?
For the
not
course,
the.
not even all the bonded terms. For the course, you must be able
Mhm.
to calculate the stretch and the bend terms. You need to know the
Okay.
form of the torsion term, that is the cosine, and how you can adjust the cosine. But I'm not going to give you a calculation of
Oh,
torsion.
okay.
Okay.
Thank you. Okay.
Okay. So, task for you: the Are You Connected quiz. Please have a look at the Are You Connected quiz, and also have a look at the prac that I've put up for you. And please email questions, contact me if you have any problems with anything. Okay.
Okay, thank you.
Any other questions? Okay.
Prof, sorry.
Yes, yes.
Okay, so that bit that you're speaking about in the beginning about like logging on to, I can't remember what it's called, Webmo or something like that.
Yes, yes, on
So
Webmo, yeah.
if we've done the Perl scripting prac,
No, this is,
and
yeah. No,
is
this
it
is
different?
this is different. Okay, the Perl
Okay,
is specifically about scripting. This new prac is only about modeling. Okay. I am going to provide an alternative to the Perl scripting prac, and that will be using Jupyter that you see on the on calcium.ru.ac.za. But please don't go to Jupyter yet. As soon as I have got that alternative to the Perl scripting available, I will post it up, and you can use that as an alternative. Yeah.
okay, so is the Webmo a third prac?
It's the Webmo is the modeling prac. The modeling prac usually is the first organic prac you ever do. So it's not
Okay,
a phys chem prac. It's normally in the context of organic chemistry. Um, so there's maybe a tiny bit of organic concepts in it, but it's counted as an organic prac.
okay, thank you.
Okay. Any other questions? Please, I am on my email all day. So if you need to contact me at any stage, or even to do a Zoom meeting to answer some questions, please contact me, and I can do that. Okay, so if there's no other questions, then I'll just say stay safe, and I'll see you at 11 o'clock tomorrow. Thank you.
Bye.